Welcome to the quantum mechanical model of the atom. Now this is just an introduction. We're not going to go in depth for how quantum mechanics works because it's really complicated. So, we know that electrons act as waves. Now, Werner Heisenberg, Louis de Broglie, and Erwin Schrödinger all emphasize the wave properties of the electron. So we already know that light acts sometimes as a particle and sometimes as a wave. And electrons bound to the nucleus seem similar to a standing wave. So here I have a little comic of a girl shaking a rope that's tied to a tree. So if we take a rope and tie one end to a tree and we shake the other end, we can set up, if we shake at specific frequencies, we can set up some standing waves in our rope. If we shake it faster, we can get additional waves shown in there. If we shake it slower, we can get fewer waves, but there's a limit to how few waves we can get in there, and we have to be shaking at specific frequencies. I can shake at one frequency to get one wave in the whole rope. I can shake at a different frequency to get two waves in the rope with one node in between. A node is where these two lines are crossing, so these two lines are basically showing the maximum, so the top and bottom, the maximum and minimum of where that rope goes. And there are certain places in the rope that basically aren't moving. They're just changing the angle as parts next to them move up and down. But there are certain places in the rope that aren't moving. So at this end, on the tree, well, that end isn't moving. And then there are other nodes in between. The end near her hand, that end is moving because she's moving it. But there are other nodes in between. So electrons bound to the nucleus seem to display things like this. Now, imagine if we took this sort of standing wave and we wrapped it around. So instead of having it go linearly like this, if we wrap it around into a circle, because remember the Bohr orbits are circular or spherical. And if we take this sort of standing wave idea, and if electrons are acting like waves, if they're in this circular orbit, then they must have orbits that are matching where when they get to the same place on the circle again, the wave has the same value. Because if we don't, we have destructive interference. So if she shakes this just slightly faster, then the rope has destructive interference and it no longer shows this nice standing wave pattern. It devolves into a jumbled mess. Well, the same thing would happen if we have electrons with a wavelength that is not some fraction of the circumference of our circle in our orbit. So, if we have a very specific wavelength, a very specific frequency, then as our wave is traced around the circle, when we trace around back to our initial point, so if we start out, say, here, and we go down and then back up and down and up and down and up and so on around the circle, when we get back to the initial point, that was this point here, when we get back there, if we hit the same point exactly, then we can keep going around again and we'll trace the same path over and over and over again as we go around. If it's slightly off, then we have a case like this, where when we get back to the beginning, we're at a different place than we were at the start. So if we start here and go up, and we go around, well now when we end, we're down there. And that means that we'll have destructive interference, and that means that this will basically end up being a jumbled mess. And what that means is that this one, an electron that has this wavelength, can't exist. This one can exist, but not that one. So what we see is that this destructive interference forces our electrons to orbit the nucleus in a path whose circumference is some whole number multiple of the electron's wavelength. So the electron has some wavelength associated with it. That wavelength is associated with how fast the energy the electron is moving, which means the energy that the electron has. So the electron has some energy, it's got some wavelength associated with it. In order to get that electron, that wave, to be mapping onto itself when we complete the circle here, that circle has to have a specific circumference to it. That circumference has to be equal to some whole number times the wavelength. We could have one wave or two waves or three waves or whatever. Which means that now we have some physical basis for why the electron is only allowed in certain orbits within the Bohr model. So, these allowed paths are called orbitals, and we can describe these orbitals mathematically using a wave function. Now, I don't want to get into the mathematics of a wave function. It gets fairly complicated. If you want to get into that, then take physical chemistry. So note that orbitals are not circular Bohr orbits. Right? They don't have to be circular. They just have to be able to be mapped out in a certain way so that the electron is not causing itself destructive interference. So we cannot predict the motion of the electron within the orbit, although there are regions where the electron is more likely to be found and regions where the electron is less likely to be found. Now, when I say we can't predict the motion of the electron, I don't mean that, oh, we haven't advanced the science far enough, or we haven't advanced mathematics far enough. I mean, it's not possible to predict where the electron will be next. Which is different than, say, if I throw a ball that direction, well, if I know where it is now, and if I know how fast it's moving, I can predict through time where the ball is going to be. But we can't do that with electrons, because electrons aren't acting like balls. They're not acting like particles all the time. They only act like particles when we look at them. But the rest of the time, when we're not looking at them, basically, they act like waves. And waves are not localized in space, like a ball is. They're diffused through space. They're not localized, they're delocalized. And so, they don't have a specific location. So they only have a specific location, the electron only has a specific location when it's being observed, when we're looking at it, or when it has to sort of make a choice, did it go this way or that way? If it doesn't have to make a choice, then it doesn't have a location in space because it's acting like a wave. So, this sort of brings us to the Heisenberg uncertainty principle. So the Heisenberg uncertainty principle says that there is a fundamental limitation to how precisely we can know both the position and momentum of a particle at a given time. Now there are other pairs, like energy and time, but we're going to look here at position and momentum. So remember, momentum is tied to speed. So it's a combination of speed and velocity, or speed and mass, so mass and velocity. So if we have some uncertainty in our position, so our x value, where our particle is, and some uncertainty in our momentum. Momentum, remember, is symbolized p, but that's calculated using the mass and velocity, so here I've split that up. So we have some uncertainty in the mass and velocity of our particle, we have some uncertainty in the position of our particle. Well, what Heisenberg is saying is that the product of these two uncertainties has to be greater than or equal to some constant, so h over 4 pi. And so h there again is Planck's constant. So what this means is that we have some value that, regardless of how good our instruments get, regardless of how well we're trying to take measurements, we can only get this product to be so low. Which means we can't ever get to the point where we know the position and momentum exactly. Because if we know them exactly, then we have no uncertainty, and that means the value here would be 0, and the value there would be 0. Well, 0 times 0 is less than this quantity. We can't have that happen. So what Heisenberg's uncertainty principle says is, the better you know the position, where your particle is, the less well you can possibly know the momentum, and vice versa. So imagine this like taking a picture. We can take a picture of a ball and know exactly where that ball was. But if we have only that picture, then we have no idea which direction the ball was moving. So we have no idea what the momentum of our ball was. So if we know our position of some particle exactly, that means that we can't know the momentum of that particle at all. And this is a problem, because in order to predict where that ball is going to go, we needed to know both the position and the momentum of the particle. Now, we can know those things to a certain extent, but we can't ever know them exactly. That's what Heisenberg's uncertainty principle is telling us, that it's not possible for us to know the position and momentum of any single particle exactly. The better we know one of them, the less well we have to know the other one. Likewise, in order for us to measure momentum, we have to know the speed of our particle. Well, in order for us to know the speed of the particle, we have to measure it at two different times. We have to measure where it is at one point and where it is at another point in time. Find the distance between them, and we know the time, so we know the average speed in there. So we can figure out the momentum of the particle, which direction it's moving, and so on. But now we're less certain about where exactly the particle is at any point in time. So this gives us a little introduction to the quantum mechanical model of the atom.